Loud. Okay. And now the most important question here is, should I crack a LaCroix or a Monster? A Monster. Okay, I'll crack a Monster. Great. Okay. All right. Where do we want to start? So I have this in sequential order, chapters 1 through 4, but we can start anywhere. Does anyone have a question they want to do? Did you even look at this packet before coming here today? No? Okay, so your brain is mush. Okay, so I will do the questions I want to do. So let's do this sig fig question, question 3. The thing about sig figs, okay, I feel like in high school when you learn sig figs, you just learn like you counted them up and then you round your answer to the smallest one. But that's only for multiplication. So we really need to be cognizant of the difference between addition, subtraction, and multiplication, division. So the best way to go about this, of course, you could just plug everything in your calculator and it spits out an answer, but that's not going to be the correct number of sig figs for that question. So we need to take it in steps. So this first part, I see it's addition, subtraction. Without even doing the math, you should be able to locate to what place value will your last significant digit be. So looking at those numbers, the answer to the parentheses should only go out to how many decimal places? 1, 2, because both values have significant digits out to the second. But I'm still going to put the whole thing in my calculator because I don't want to throw away that, point, 294. I don't want to throw away that 4. I'm still going to put the whole thing in. So let's see what my calculator says. 12.11 minus 3.294. That operation is 8.816. But we only know out to 2 decimal places. So that whole parentheses only has 3 sig figs. But again, I don't want to throw away that 6 yet, right? Because that's like throwing away money. So we don't want to throw that away. The next part here is, again, addition, subtraction, but it's a little bit different here. I have some scientific notation. All right, and so it's another addition, subtraction. This one looks a little bit different. I don't really like adding numbers that are both scientific notation and regular notation. So I'm gonna make it easier for myself and rewrite this number into like a normal number. So 10 to the 1 is just 10. That 1 has infinite sig figs. It's a counting number. So I'm just gonna undo this scientific notation, and this is better known as the number 20. But writing it as 20, like if you put that in your calculator, it's gonna spit out 20. But is it 20? No, it is 20.00. And so now the numbers look good enough that we can like add and subtract like normal. So these are the 2 numbers we're adding, this one and this one. If we add them up, to what place value do we know out to? The second decimal place, yeah. So I think I can do this in my head. It would be 22.256, but we only know out to 2 decimal places. So this number has 4 sig figs. And now, after I've done all the addition, subtraction, I can see everything is now multiplication, division. Now you are allowed to just count it up and take the lowest one. So based upon all these numbers now that I've rewritten, my answer should have how many sig figs? 3, yes, 3 sig figs. So whatever that answer is gonna have 3 sig figs. All right, I like this question because look at all the numbers. Look at all the numbers in the original question. Do any of them have 3 sig figs? No, they don't. So if you fall into the trap of just counting it all up, like, getting sig figs in each number and rounding your answer to that, you'll be wrong in this question because you're not taking into account addition, subtraction, unfortunately. So, good. So my answer is 3 sig figs. I don't know what the answer is. It's on the key. Yeah.
I feel like you've got a lot of the ones that are like just specifically sig fig. Are there going to be any that are like this layout of sig fig thing? Is it going to be like fixed about the problem?
So I'll just straight up tell you that numerical questions, I cannot ask sig figs. So usually have you tried a practice exam yet?
I think
Okay, yeah, no, that's fine. So the practice exam, the Carmen style one, there are some numerical inputs in there, and usually in the numerical input questions, I specifically tell you what place value to report to, because computers are stupid and they don't do sig figs well. So those types of questions, I usually put a tolerance on it, and so you reporting the wrong sig figs isn't a big deal. But when it is a big deal, I usually will say report to the correct number of sig figs. Yeah. Yes. So for this question, it would not be a numerical. It would be a multiple choice where I would have, okay, let's actually do the math. All right, so these are what the options would be. So 1822.256 divided by 15.85. Okay, so the answer is 12.4, I think. All right, that's what my calculator says. But, okay, so that's gonna be A. B is gonna be 12.38. All right, that's if you thought that, you know, it has, every single number here has 4 sig figs. So that would be the next, I guess, plausible answer. I would do an answer where you rounded each step. And so it might be a different value. It might be rounded like 12.42 or something. Maybe you rounded each step. I don't want you to round in intermediate steps. And so I'd put the pre-rounded number answer in there as well. And then I would, you know, do a 5 sig fig one, like a D would be 12.379 or something like that. Does that make sense? Yeah, sig fig questions are kind of hard to do on a multiple choice. Cool. All right. Another type of sig fig question would be like number 2. How many values in the following list have 3 sig figs? So just inspecting every number. That first number has how many sig figs? 1, because those zeros don't count. The next one has how many? 3, yes, because that 1.02, that 0 is measured, so it's 3. The next one, it's an operation, so I actually have to do it. So 92 plus 87, so it'd be 179. So that also has 3 sig figs. This is addition, so I do know out to the ones place, so that one has 3 sig figs too. And then that last one has how many sig figs? Also 3, yeah, so 3 of them have 3 sig figs. So this could be a multiple choice question too, where I give you a list of numbers and I say, you know, how many have X number of sig figs? Oh no. Oh, what if I put 3 cats? Or no, what if I put 123 cats? Yeah, is that 3 sig figs? But it's 123. How many sig figs does it have? Infinite, yeah, because you can count that, like actually count it. So that would be infinite sig figs. Cool, all right, are we good with sig figs? Yes, all right. Okay, let's do this one. Let's do 4. In lab, you take the mass of a solid cube. It has that mass. This cube has a side length of 13 millimeters. What's the density? And what is the identity of the solid cube? Do I give you density? I do give you density. Look how nice. So density is mass over volume. So I need to figure out the density. Density is also an intensive property. So if we know the value, we can compare the metals and their densities to figure out what it is. And so it looks like they give us the mass, so that's great. In the numerator, I just need to figure out the volume. So they give us a side length of 13 millimeters of a cube. Do we know the volume of a cube? How do we get the volume of a cube? It's length cubed. Great. Great. We don't do crazy math here. All right. So if I take 13 millimeters cubed, I get a number. Whoops, 13 cubed. I get something like the volume of the cube is 2,197 millimeters cubed. But there's a problem here. You know, if I just put the mass given over the volume, I just calculate it, it would be in grams per millimeter cubed. I don't want that. All of these densities are in cubic centimeters, so I need to convert that millimeter cubed to centimeters cubed. I don't know what the conversion is between millimeters cubed and centimeters cubed, but I do know the conversion between millimeters and centimeters, or meters and millimeters. So the way that we approach this is I know that there are 1,000 millimeters in 1 meter, but I need to do that 3 times. But now I'm in meters cubed. I want to get to centimeters cubed. So 1 meter is how many centimeters? 100 centimeters. But again, because it's millimeter cubed, you want to cube the whole thing. All right, and then that will give us how many cubic centimeters our cube is. I already did this wrong. 2197 divided by 1,000 cubed divided by, or no, times 100 cubed. So I got that this cube equals 2.197 centimeters cubed. And so then that value goes into my density calculation. So 5.8589 grams over, 2.197 centimeters cubed. And then I get some answer. Is that right? That doesn't look right. Is it right? Oh yeah, okay. And then my answer is something like aluminum, 5.8589 divided by that. 2.66 grams or 67 grams per centimeter cubed. All right, and so that would tell me that it's aluminum because it's closest to aluminum. Sig fig wise, I would say this would actually be 2 sig figs because the length, which is measured as 2 sig figs, and all of this was multiplication. So I should really report 2.7 grams per centimeter cubed. Another way you could have done this, does anyone know how many millimeters are in a centimeter? 10. Yeah, so there's a slightly quicker way to do it as well. If you did that, you're essentially just combining these 2 steps. That works too. So what I'm talking about is you start with 2197 millimeters cubed, and as long as you know there are 10 millimeters in 1 centimeter, this works the same. Mathematically, it's the exact same. Okay. But you don't have to know that. As long as you know milli and centi, then you're good too. You just have to do it in 2 steps, using the base unit as kind of like home base to get where you need to go. Okay, all right. I want to do question 6 because I wrote it and I was pretty proud of it. Because it's winter right now, and soon it'll be spring, and I tap maple trees to make maple syrup in the early spring. Yeah, it's a lot of work. And so I wrote a dimensional analysis question about it. Okay, so how many 5-gallon buckets does Dr. N need to collect to make 12.5 ounces of maple syrup? The density of finished maple syrup is this. So it looks like there's a lot of conversions here. Assume the density of maple tree sap. So that's what I tap out of the trees. It's like slightly sugary, but not as sugary as maple syrup. You gotta like boil it down to concentrate the sugar. The density of maple tree sap is 1 gram per milliliter. The sugar content in finished maple syrup is 66% sugar by mass. So I should say that, I should have said that, by mass. The sugar content in fresh maple sap is 2% sugar, and 1 5-gallon bucket can hold 5 gallons. And then I give you some conversions here. A gallon equals 128 fluid ounces, and 1 fluid ounce is 29.5 milliliters. Okay, there's a lot of information there. It's easy to get lost. So I would suggest taking every single piece of information and making an equality. You set something equal to something else. Once you gather all of them, then you can put together the pieces of dimensional analysis to get to the unit you want. So let's look at the density. The first thing I highlighted here, how can I rewrite that number into an equality that is more useful to me? Maple syrup is 1.37 grams of it equals 1 milliliter of maple syrup, of finished maple syrup. That's the density. Of the sap is different. It has a different density. It's not 1.37 grams, it's 1.0 grams of sap is 1 milliliter of sap. It's the fresh stuff that comes out of the tree. All right. And the next one here, the sugar content in finished maple syrup is 66% sugar. So this is syrup again. So how can I write an equality from a percentage here? 66% sugar. If I have 100 grams of syrup, how much of it is sugar? How much of it is sugar? 66 of it is sugar, 60 grams of sugar. All right, and the next piece of information, the sugar content in fresh sap is 2% sugar. So that means for every 100 grams of sap, I have how much sugar? 2 grams of sugar. Great. And then I have some equalities here, fluid ounce and gallons and stuff like that. Okay, so where do we even start? So they give me, all right, I want to make 12.5 ounces of syrup. So I'm going to start with that, 12.5 ounces of syrup. I want to figure out, you know, how much sugar is present in there, and then I can work my way up to figure out how much sap I need. So I'm going to convert that to milliliters because all these densities are in milliliters, and I'm given that information that 1 ounce is 29.5 milliliters, but note here that I'm in the unit of syrup. So what equality here will be most useful to me, given the unit I'm in right now? I'm in milliliters of syrup, so which one do I want? This first one, second one, third one, fourth one? The first one, yeah, because this is the density of maple syrup, where it says 1 milliliter of it is 1.37 grams of syrup. So let's use that one. So 1 milliliter of syrup is 1.37 grams of syrup. So we're still in the unit of syrup. Okay, cool. What should I do next? Are there any other gram amounts of syrup in my equality toolbox I have? The sugar content. This is the one I want to use next. So don't try to use the next density of sap, because this is mass of syrup and this is mass of sap. We can't, those don't intermix. So what I actually want to do is use this third equality and say that, okay, for every 100 grams of syrup, there is 66 grams of sugar. So now I'm in the unit of grams of sugar. What equality do I want to use next? The sap to sugar, yeah. So, but where am I going to put that to? On the bottom, yeah. So 2 grams of sap, the sugar in the sap one is 100 grams of sap. That comes out of the tree. So interesting, we like multiplied by the one percentage, but then we divided by the other percentage. And dimensional analysis is what allowed us to, you know, understand that. All right, so now we have grams of sap. Then if we get to volume, all right, so we're just assuming it's one gram is 1 milliliter of sap, so 1 gram of sap is 1 milliliter of sap, and then we're just a little bit further and we can get to gallons. So now we're in milliliters, so I'm gonna convert that milliliters to fluid ounces, so 29.5 milliliters on the bottom, 1 ounce up top, and then 128 ounces is 1 gallon. So the hardest part was like the middle part, being able to relate sugar content of one substance and using density to get you know, relate it to the sugar content of the other substance, and then working your way back up to a reasonable volume. Did anyone calculate it? Calculating it? How many gallons? 4.4 gallons. Oh, we forgot one more conversion, because I asked you how many buckets do I need? 1. Yeah, so the last conversion is 5 gallons is in 1 5-gallon bucket. 1 5-gallon bucket. That was supposed to be a funny thing, that I put in the question, but I don't know if you think it's funny. So one bucket of sap, if I collect that, should be able to make me one $5 bottle of maple syrup. All that work for one bottle of maple syrup. So that's a harder one. I try to come up with a harder one. Do you think you would be able to do that on an exam? This one? Yeah? Okay, good. Do you actually do these steps with the equals and the equal sign? Do you do that? Or do you just look at the unit and know whether you have to multiply or divide? Once you do it enough, then like you don't have to do it anymore. But I do suggest, if you don't even know where to start, working out those equalities will help you see how the units can fit together to get to the thing that you want. Okay, what's next? I'm done with chapter 1. What chapter do you want to do? Someone just say a number. Chapter, oh my gosh, they're so boring. They're so boring. This is how Matt felt, right? In those reviews. Yeah. Okay. I like questions like this, right? Which of the following atoms or ions possesses exactly 20 electrons? Because we have to figure it out for all of them, don't we? Don't we have to do all of them? Yeah, instead of me just asking like, how many electrons does neon have? And then you just look at the periodic table. Nope, we have to look at all of them. All right, so what are the 3 equations that we use to get us through the subatomic particle stuff? There's 3. The number of protons comes from what? The atomic number. Yeah, so the identity of the thing. All right, and how do we get number of neutrons? It's not the atomic weight. It's the mass number. Let's be specific with the terminology here. Mass numbers are the whole number that's in the corner. All right, so I actually want to rewrite this. Neutrons plus number of protons equals the mass number, because those are the only subatomic particles that have weight. Electrons basically don't weigh anything. Barely any. They're still particles, they just don't weigh that much. Right? And then the last one is that the overall charge of the substance will always be the number of protons minus the number of electrons, because they're negatively charged. So let's just get all of them. So we need protons, we need neutrons, and we need electrons. Actually, we don't need neutrons to figure out the neutrons to answer this question, but let's do it anyway for completeness. So the element will tell us what how many protons everything has. So neon has 10, magnesium has 12, sulfur has 16, calcium has 20, titanium has 22. And so then we get number of neutrons by subtracting the mass number that's in the corner for all of these by the number of protons, because the rest of the weight will be neutrons. We don't technically need this to answer this question, but let's just do it anyway. So 10, 12, 18, 20, 24. Okay. And then the last one is number of electrons. So we actually want to compare the number of electrons to protons and compare that to the overall charge of the substance. Neon doesn't have anything written, no charge written on it. So what is its charge? Neutral, yeah, so it's 0. So when something's neutral, the number of protons and electrons are equal. So 10. So that's not my answer. Magnesium here, it's a 2+ cation. So I like to just think there's more protons present. So I have less electrons, so 10 electrons present. Yeah, or you can use the equation, whatever. I just know electrons are negatively charged, protons are positive. Sulfur here, how many protons on that? 18, yeah, because it's a -2 charge, so you need 2 additional electrons to balance that out, because we can't change protons at this point. Protons relate to the identity. I see that a lot with my 11, 10 kids or students. They will try to change the number of protons, and I'm like, you can't do that, because it's already that element, you can't change it. So all we can do is change electrons to adjust charge. And then so calcium here has how many electrons? 18. And then so my answer has to be titanium, which it is. It's a 2+ charge, so there's 2 more protons, so the answer is 20. So there's the answer. And so this question's nice because there's a lot of 20s bouncing around. So if you are unsure how to get number of electrons, or if you think, number of neutrons, or this mass number 20 is the number you're looking for. No, that's our mass number. Then there's a lot of places where you can go wrong in this example. Good? Okay, all right. Okay, copper is made up of 2 isotopes, that and that. What is the atomic mass of copper to the correct number of sig figs? See how I said correct number of sig figs? Yeah. All right, so this is a percent or a weighted average example. I cannot just take the 2 masses, add them up, and divide by 2. Because if you do that, it's an equal weighted average where you're assuming each weight contributes 50%. Those are the averages we know and are used to. A weighted average weights each component differently. So here I tell you that copper 63 is 69% abundant, but I don't give you the abundance of 65. Is that a problem? No, it's not. How do I get it? It's just what's left over. So copper 65 will have a percent abundance of 30 point, I don't know, 152. Okay. 30.848%. All right, and so at this point you just multiply each of the masses by the percent abundance, but just make sure it's in a fraction form, and then add those 2 up. So putting that together, so our weighted average for copper, and of course this is synonymous for atomic mass, is us doing the weighted average work. So atomic mass is 62.9296 AMU. I'm going to just drop the units because I'm lazy. 0.69152, that's my fractional abundance. Then 64.9278, and then 0.30848. Okay, so this is a mixed operation again, and I told you to check sig figs, unfortunately. So let's look at the multiplication first. These 2 numbers, when I do the operation, should be reported to how many sig figs? 5, yeah, because this is multiplication. I do the multiplication first. So this, I'm limited by that abundance. So this is going to have 5 sig figs, whatever that answer is. What about the second term? Also going to have 5. So I just like to keep that in mind before I actually do the math. So 64.9278. So this quantity is 20.0289 3. I'm just going to keep a couple extra digits, and then so that would be rounded to 5 sig figs there, and then 62.9296 times 0.69152 is 42.8877. So 5 sig figs there. Okay, so now it's addition. So to how many decimal places can I report my answer when I add these 2 up? Yes, to 3 decimal places, because that's, each of them are known out to there. And so add those up. Hopefully I got this right. So 20.02893, I get 63.917 AMU. So that is to 5 sig figs. 5 sig figs. So I didn't do any tricky stuff here where the sig figs change or something. No. Good. Now, what are we right? What is the significance of this atomic mass? It's the value that's on the periodic table, because all of these values are collective, weighted average masses because we're never working with like one isotope, one atom. We're always working with a huge sample of copper atoms that has a, percent abundance of each isotope. Are we right? 63.546. Why am I so off? My 42 is a little. Okay. 62, did I put the numbers in right? 62.9296 times 0.69152. Yeah, I'm super wrong there, but the sig figs are still right? Okay. 63.5171. Okay, and so now with the right number, does it match the periodic table? Okay. Isn't that nice? Isn't that kind of satisfying? Or no? What? Didn't I give an example? Yeah, I can just give you an unknown and just give you random numbers so you can't check it. Of course not. I'm not going to make it so you can just pick the number off the periodic table. Of course not. But what would be the purpose of finding it? No, I'm assessing you on, do you know how to take a freaking weighted average given information? That's what the assignment is. And so I can just make up something. I think one of the practice exams said like indium has two isotopes, indium 113 and indium 115, and I ask you which one's more abundant. Do you know where to start? What does that do for me? So tell me what number. So tell me the number. Where's your handout? Okay, someone tell me the math. 114 point what? 818. Okay, what does that number do for me? There you go. Yes, it's closer to 114 or the 115. There we go. Yes, good job. Okay. All right, next one. Which of the following metals is in the same group as sodium? Did you just say hydrogen? Okay. It's in the same group. What does group mean? Group means column, yes. What? Yes. No, that's fine. That's fine. I actually didn't know that I put hydrogen as a distractor. No, I would say if you're going to get this question wrong, you would say hydrogen because it's in the same column, right? It's in the same column as sodium, but what's the problem with hydrogen? It's what? It is crazy, yes. It is not a metal. That's the distractor here. So the correct answer is what? Rubidium. And did you see how I put names here? I didn't actually put symbols because I'm evil. And so what is aluminum? How are aluminum and sodium related? How did I try to trick you here? It's right. Yeah, that's how I trick you. Yeah, it's in the same period because it's in the same row. And then what about silicon? It's same thing. It's in the same group. So how can I change the question so silicon would be the right answer? How could I actually change the wording in the question? Which of the following blank is in the same blank as sodium? Yes, metalloid in the same period. Yes. What? Yeah. So those are all the ways I can change this question to trick you, right? Because if it was period, right, the aluminum and silicon would be technically in the same period, but how we distinguish those two is one's a metal and one's a metalloid. Okay. What are we whispering about? But ask yourself, see, try to be a teacher. Like, what is that assessing? What? Yeah, right. What's my favorite element?
Oh, 10. Wait, antimony.
Yes, antimony. Yes. Yes, antimony is SB. Do you have to memorize that one? Okay, good. Well, tin is what to antimony? Yes, it is SN. Is tin what? Is a what? Tin is in the same blank as antimony. It's in the same period, yes. Okay, good job. All right, what's the name of these things? Okay, so remember how we name things. There's two categories, ionic naming and then molecular naming. Ionic name, how do you identify something that's ionic? It has ions. Typically, it's a metal and a non-metal, or a metal and a polyatomic. Do we know our polyatomics? Please tell me. Yes. So what is CO3? Carbonate, good. So what is the name of this thing? Zinc carbonate. Right, so you were trying to put a number on it, right? Yes, because it's a transition metal. But zinc is one of the exception transition metals. Yeah. So if you look at the periodic table, right? Okay, there's my periodic table. Like all the transition metals typically need a Roman numeral to say the charge, except zinc, silver, and aluminum. Those three like metals always have a fixed charge. Silver as an ion is always silver 1. Zinc as an ion is always zinc 2+. Aluminum as a cation is always 3+. So we actually don't need to tell the reader what charge it is because they always adopt those charges. It's the next one, copper. So we do need to tell the reader what the charge is. So this would be copper nitrate, but we need to say the charge. Yeah, so it would be 2. And you also don't know the charge of carbonate. It's 2-. So yeah, do know that. So this would be copper 2 nitrate. All right, what about the next one? How do we name that? Is that ionic? No, all nonmetals. So we just use molecular naming where we just say how many of each atom there is. So this is phosphorus, pentafluorine, fluoride. Yeah, so whatever the second element is gets the "ide" ending, but the first element just is regular. Okay, what about the last one here? Sodium chlorite. Yes, so sodium, I love ionic things because you just say the cation and then the anion. Sodium, ClO2, is a polyatomic. So in my brain, to try to memorize the least amount of stuff, I know that chlorate is ClO3-. And so since there's one less oxygen, this is chlorite. If it was ClO4, it would be perchlorate. So I remember the base, like the parent name, and then use the rules to get all the cousins. Does that make sense? Okay. Do we have more? Okay, more. Let's do the formula from the name. And so same idea, you want to identify, is it using molecular naming or ionic naming? So sulfur hexafluoride, what kind of naming is that? Yeah. So it's SF, what is hexa? 6. Ammonium sulfate. So this is ionic because it's using ionic names. So the tough thing with ionic things is you need to first identify the ions involved and their charges, and then combine them in such a way so they are charge neutral. So ammonium is what? Remember, you need to know formula, name, and charge. It is N, not NH3, 4+. Yes, so you're confusing ammonia, but they're related, okay? There's ammonia, like the smelly, like Windex, like the active ingredient in Windex is ammonia. That's NH3, it's neutral, versus ammonium is a cation. Ammonium. They are related to one another. Okay, so there's ammonium, and then sulfate is what? SO, how many? 4 charge? 2 minus, yeah. So this is, so we need to make it charge balanced. So this is NH4. I need 2 of them to balance 1 sulfate. To memorize some of the ionic, the polyatomics, I actually like to memorize the acids, because sulfate is SO4 2 minus, right? So how many hydrogen pluses will it pick up? 2 of them, so it's H2SO4. Sulfate is 2 minus. Phosphoric acid is a triprotic acid. So what do you think the charge is of phosphate? 3 minus, yeah, so H3PO4, its phosphate is a 3 minus. Nitric acid is just HNO3, and it's a 1 minus. So I don't like to have memorized both those things in my brain, so I just combine them. That's, yeah. And then of these, which ones are strong acids that I wrote? Because we did learn about strong acids too. The sulfuric and nitric are both strong. Okay. Lots of stuff. Y'all, when I say memorize something, like make a little note, make your flashcards, like write them. Write them. Okay. All right. Consider the balanced chemical equation for the complete combustion of this. But Dr. N, that's just a bunch of lines. There's nothing there. Okay. What do I do with this? You just carbon everything. Yeah, then you do the H's. So where are my carbons? Every point and N. So there's a carbon, there's a carbon, there's a carbon, there's a carbon, there's a carbon. So this is 1, 2, 3, 4, 5. So there's 5 carbons. Then hydrogens come from where? The intersections, yeah, but what's the detail? How can we fine tune where how many hydrogens each carbon has? 4 bonds. So how many hydrogens does this carbon have? 3. 1, 2, 3. Then the next one, 2. Then the next one, 1. Then the next one. It doesn't matter, they're the same. 3. I was thinking that too. I was thinking ahead, and they're the same. So that's how many hydrogens there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. H12. Okay. Stop with the 2n plus 2. Stop with the 2n plus 2. Yes, does the 2n plus 2 work here? Yes, it does. But I can just draw something else, right? I can draw this. 2n plus 2 ain't gonna work there. No, but if you just follow the frickin' method, all right, it'll still work. How many carbon or hydrogens are on that carbon? 2. How about this one? 2, and this one? 1, this one? 2. It's okay, we're going fast. How about this one? 1, yeah, because there's a double bond. What about this one? 1, and then the last one. 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. How many carbons are there? 1, 2, 3, 4, 5, 6, 7. Does your sweet little 2n plus... You want to take that chance? I hate 2n plus 2. I hate it. I hope you all do 2n plus 2 and... Okay, all right, we didn't even answer the question yet. Okay, what is the sum of all the coefficients when we balance it? So that's the thing we're burning. So if this is combustion, what's my reactant? Other reactant? O2, and I make CO2 and water, all right? And then you follow my fail-safe strategy, which is you balance the carbons first with CO2. Then you balance the hydrogens, excuse me. So you need 6. And then you take inventory of the oxygens and you just fill the void with the coefficient before O2. So on the product side, there are 10 oxygens coming from CO2, 6 coming from water, so that's 16 oxygens. So I just need to ask myself, how can I make there be 16 on the other side? So if I put 8 oxygens, then I'm done. Okay, so then what is the sum? 20? I don't know. So there's a 6 plus 5, so that's 11 plus 8, and then do not, for the love of God, don't forget that 1. So it's 20. Yes. Do we like questions like that? You do? Even if you have to count carbons like that? In a little weird way? It's not weird. It's carbon always makes 4 bonds. So. What's our favorite chapter? 4? 3? Conversions, math? No. Okay. All right, let's balance this thing. I don't even know what the answer is. So we got potassium, oxygen, hydrogens. This one's a little bit tricky because there's hydrogens here, but there's actually hydrogens in 2 spots on the product side. So this is my trick when it looks confusing like this. Let's use logic. There has to be an even number of hydrogens on both sides because, right, there's a coefficient in front of water, so it has to be even. So this single hydrogen on this KOH is gonna mess us up. So I'm gonna fix it by just putting a 2 in front of it. Because if I do that, then I will have an even number on both sides. You following me? That's like the only way I can kind of get it to balance. But now I messed up potassium. So I have 2 potassium. So if I put 2 KO2s, then that fixes the potassiums. What am I going to do now? I'm going to check. I'm going to leave this oxygen for last. I'm going to leave that oxygen for last because it's going to be easy to balance and I won't screw everything else up. So I'm going to look at the hydrogens now. There's 2 hydrogens here. There's 2 here, there's 2 here. So there's a total of 4 hydrogens on the product side. So if I put a 2 in front of water, then now the hydrogens are balanced. Great. And now I just have to make up the difference of the oxygens that I produced. And again, keeping the simplest thing for last is a good trick because you don't screw up everything else. What's the coefficient? 1, 2, 3, 4, 5, 6. 7, 8, 9, 10. So 5? Is that right? 4. Okay, 4 hydrogens there. 2, 3, 4. Yeah, okay. 4 plus 2. Oh no, that's not right. I'm dumb. 4 plus, so there needs to be 6. So 1, 2, 3. Okay, no, that's just a 1. All right, there we go. Good. It's late. Okay, so 2, 2, 2, 1, 1. Okay, good. All right, next one. Which solution has the greatest concentration of ions? When you dissolve salt in water, NaCl in water, what makes it conduct electricity? Why did it glow? Yeah, electrolytes. What are the electrolytes in NaCl? You get what? When you dissolve that in water, what do you get out? You get a Na plus. What's in my monster? Just a bunch of vitamins, right? Yeah, it's electrolytes, a bunch of electrolytes to keep me going. But in the solid form, right, they have these neutral ionic compounds, but once you dissolve them in a delicious beverage, you get the ions, the free ions. They break apart. Okay? Ionic things break up into their constituent ions, kind of like undoing the naming that we did, right? So this substance, see they're all the same concentration. Okay, I tried to do that. So this solution will break up into 2 moles of ions. This substance, when you dissolve it, what does it break up into? If we were doing like the net ionic equation and we broke this up, what would you get out of it? You would get out a iron, try to name it, 3+, and then what else do you get? A Cl-, but 3 of them. So you put one thing in, how many ions do you get out? 4. What about this one? How many ions do you get out of potassium phosphate? 3, 4. Yes, you get K+, 3 of them, and then a phosphate. The tricky thing in this one is that some students will think that phosphate breaks up. They'll think that you get a P, you get O's, you get ions out the wazoo, but you don't. Phosphate stays together. It's polyatomic. And then the last one, you get 2 iron, 3 pluses, and you get 3 sulfates. So which one has the most ions? More ions means more conductivity. Good. If we were doing the example of HF and HCl, so 1 molar HF, 1 molar HCl, which one's going to conduct more electricity? What, same? HCl, yeah, this one's different. These are acids. So their electrolyte behavior is dependent on what kind of acid it is. Strong acids are strong electrolytes. So HCl will break up fully. HF does not break up fully because it is a weak electrolyte. Versus like, so HF, if I had NaOH, so 1.0 molarity NaOH, and 1.0 molarity NH3. Same idea here. Sodium hydroxide is a strong base. Also, it's ionic, so it's fully going to break up, but ammonia is actually a weak base, so it's only going to partially dissociate. So the weak things conduct electricity less. Don't you remember the demo? The very weak light versus the strong light. Okay, good. All right. Which of the following reactions leads to a precipitate? How the heck am I supposed to know? So in this type of question, we need to predict the products and see if they are insoluble or soluble or not in water. So if it's insoluble, then you will produce a precipitate. So in this case, you need this, okay? Because I do not expect you guys to just memorize the solubility table. Yeah, but it's on here, okay? It's all on there. So how do we predict the products? You just swap them, right? You swap ions here. So copper goes with hydroxide, calcium goes with chloride. So I actually don't need to balance anything. You can just look at your table. I would look at, okay, hydroxide are typically insoluble, and copper is not an exception. So I would form the solid copper hydroxide. And so reaction 1 does produce a precipitate, a solid. You can check the other substance, calcium chloride is soluble. Most chlorides are soluble, including calcium chloride. So that will be aqueous, but I don't need to write that. I just need to figure out which one is a solid. That's what I care about. All right, so then if we do the swaparoo with the next one, what do I get? I get calcium carbonate and sodium nitrate. All nitrates are soluble according to this table. So I know that that one's going to be aqueous, but calcium carbonate, what is that? Is that soluble, insoluble? You're just gonna let me do the work? Yeah, okay, great, insoluble. Yes, because if you look at carbonates, they're all mostly insoluble except a few exceptions. So calcium carbonate is our solid. So hopefully at this point, you'll see the answer will be all of the above, but let's just check to make sure that the last one does have a solid. Iron iodide iron and iodide looks like is soluble because iodides are typically soluble and iron is not an exception. But if we look at barium sulfate, sulfates are usually soluble, but barium sulfate is an exception. So barium sulfate is a solid. So please understand how to work that table. Yes. So those are my solids that I make. And of course I make aqueous things, but I don't really care about those. Cool. But those things that are aqueous, what do we call those things when we write our net ionic equation? They're the spectator ions. Yep. Because they're aqueous on both sides. Okay. All right. 15. Oh yeah, let's do this. Well, let's write the balanced net ionic equation for sodium carbonate and calcium chloride. So we have to do this all over again. So we're combining these two substances, aqueous plus calcium chloride, aqueous, and we need to predict products. So we're going to do the ion swaparoo. So we get a calcium carbonate. And we get a sodium chloride. So you might notice like there's 2 sodiums in the formula, there's 2 chlorides in the formula, but we want to write the empirical formula here for ionic salts. We should just write NaCl, but put a 2 coefficient in front. We don't want to put Na2Cl2. That's not how we write salts. We always write it in the simplest form. And so the last step here is to determine what are the states of our products. And so we use the solubility table again. So calcium carbonate is what state? Solid, yes. NaCl is what state? Aqueous, great. Okay, is that my net ionic equation? No, we need to figure out our spectators. And in order to do that, we need to write our total ionic equation. All right, so we need to identify, we only split things that are 2 things. They have to be 2 things. They have to be 1, aqueous, 2, a strong electrolyte. So we go through all of these. So is this first thing aqueous and a strong electrolyte? Strong electrolytes include all strong acids and all ionic compounds. So does sodium carbonate, is that either of those things? Yes, it is what? Ionic compound. And it's aqueous, so we split this guy. All right, do we split calcium chloride? Do we split that? What's our criteria? It has to be aqueous and a strong electrolyte. Is it those things? Yes, it is. So we split it. What about calcium carbonate? Is it ionic? Yeah. Yes, it is ionic, but what's the problem? It's solid. So do we split it? No split. What? Why are you guys giggling? No split. What about NaCl? You split it. Okay. So if we split all these things, all right, we actually have to split it into their full ions. I know this is a lot of work, but once you do it like a dozen times, you'll realize like kind of what happens here. So we have 2 Na pluses. I'm gonna just drop the states. We have a carbonate. We have a calcium 2 plus. We get 2 chlorides out. We no split calcium carbonate. Do not just split everything. If you split everything, you'll see everything's a spectator and you'll be sad because everything just cancels out. So don't split that. Okay, keep that together. And then we split those NaCl. So we get 2 Na pluses and 2 chlorides. So you see what's our spectator ion? This is spectator ions. So you need to look at every single ion and just track it from the reactant side to the product side and see if it changes. If it does not change, if it's the exact same on both sides, it's a spectator. So does sodium change at all? Going from here to there? No, I literally wrote the exact same thing twice, so it cancels out. That is a spectator. Is carbonate a spectator? No, because now it's all tied up in a calcium carbonate. It did change. And then calcium also changed. So chloride is our other spectator. So if you rewrite it without that, then that's our net ionic. Cool. All right, so let's do one more. Net ionic, mixing an acid and a bit, yeah. Will what be aqueous? They should. So what a net ionic equation tells you is exactly what's happening in the reaction. If you do this reaction, you mix something that looks clear, something that looks clear, you mix it and you get a solid. So what you're essentially doing is you're bringing calcium ions and carbonate ions together and you're making a solid. And that's what this equation is trying to tell you. You're bringing together two ions, forming a solid. So I'm not going to say every time it's ions on the reactant side, because this next example, there's not all ions on the reactant side. So let's do it. Okay, so I'm just going to write the balanced equation. I don't want to wait for you guys. All right, so this is an acid-base reaction. We still just swap ions. Everything's just a 1-to-1 ratio here. All right, so in a acid-base reaction, what is our product? What are we forming? Water. Because you're combining this H and you're combining it with an OH. HOH is better known as water. And then our other product is sodium nitrite, NaNO2. And that is, if you look at your solubility table, is soluble, aqueous. Okay, so there's my balanced equation. So let's get the total ionic. Let's work left to right, or right to left. Do we split sodium nitrite? Why do we split sodium nitrite? It's aqueous and it's ionic. So yes, we split it. Do we split water? No split. Why? It's a liquid. Do we split sodium hydroxide? Ask yourself, what's the criteria for splitting? It has to be a strong electrolyte and aqueous. It's aqueous. Sodium hydroxide is also a strong base. It's also ionic. So yeah, we split that guy. All right, what about the last one, nitrous acid, HNO2? Remember the criteria. It has to be a strong electrolyte and aqueous. Is it aqueous? Yes, but is it a strong electrolyte? No, it's not. It is a weak acid. So no split. If I replaced it with like nitric acid, it would be a yes split, but this is nitrous acid. It's not one of our 6 or 7 strong acids, so we don't split it. So this one's a little bit different. I'm gonna just skip some steps and I can see I split NaOH and sodium nitrite, so I know that sodium is a spectator because I'm splitting both of those, so I'm just gonna skip a step. So we do not separate the weak acid here, all right, but we do get that hydroxide out and we get water because that's not part of our spectator, and then we get that nitrite. Yeah, I skipped some steps. Oh, there's aqueous. They're aqueous there. So in this example, only sodium is our spectator because we did not split the nitrous acid. So spectator. So I think we did an example like this in class where it was like HF or something. All right. Okay. All right, next one. What is the percent nitrogen in this guy? Well, let's name this. What's the name of that? Ammonium sulfate, yeah. Cool. This one's interesting because I told you the trick for ionic compounds is like a metal and a non-metal. You look closely here, ammonium sulfate is actually made of all non-metals. So you might think initially that it is molecular, but it's not because it's made up of ions. Ammonium is one of the ions you need to know. Sulfate's one of the ions you need to know. So it's an ionic compound, even though it's all molecular, all non-metals. So that's kind of interesting. Okay, what is the percent nitrogen in this? So how do we calculate that? We need the mass of nitrogen in the compound, and then we need the total mass of the compound. So probably the best way to do this is just take inventory of the elements and calculate the molar mass. How do we calculate a molar mass? We use what? We memorize it? No, we use our periodic table, but be very careful about counting things, okay? Because look at the formula. How many nitrogens do I have? 2. There's 2 nitrogens. How many hydrogens do I have? 8. And then I have 1 sulfur and then 4 oxygen. So we need to multiply those respective things. So 14.0, I'm just going to round 1 times 2. For the nitrogens, I have 8 hydrogens, so 1.008 times 8 of them. I have a sulfur, I think it's 32.06. The sulfur, and then 4 oxygens, 4 times 16.00. All right, and you add those up. Does someone have it? The molar mass of the whole compound is You want me to do all the heavy lifting? I'm waiting for them. 132.144. Great. So that's of the whole compound. So that's my denominator. So mass of nitrogen. Am I just going to put 14 up there? No, I have to put 2 times 14 because there's 2 nitrogen atoms in there. So 2 times 14 over the 132, and then times 100, whatever that answer is. Maybe I should just have my key. 18. It's like 21.2%. If you look at my key, I have the whole, the one with the 6 sig figs using the actual big numbers, but yeah, I got 21.20%. Something like that. Is that what you got? Okay, good. Okay, next one. So we're still in, are we in chapter 3? Yeah, chapter 3. Okay. Magnetite is an oxide of iron, and it contains this much iron by mass. What is the empirical formula of iron oxide? Empirical formulas. I love these. Either you love them or you hate them because it's, yeah. What's the strategy here with empirical formulas? You need to start with what? Gram amount of elements, then you need to convert to mole amount of elements, and then that will help you get a mole ratio. So they give me a percent, not a gram amount. So what's a good strategy to use? 100 what? Of iron? Right, yes, we're going to assume you have 100 grams of sample, yes, because then that percentage just turns into grams of iron. So we have 72.4 grams of iron. Okay, now what? I need a gram amount of the other thing, don't I? Where do I get that? It's the rest of it, yes. So, because if it's a 100-gram sample and there's only iron and oxygen, the rest of it has to be oxygen. So that's 27.6 grams of oxygen. All right, so once you're at this point, you convert grams to moles. Yes, so we use molar masses of those respective things. So iron is like 5.845 grams is 1 mole of iron, equals something. And then oxygen is divided by 16.00 grams, 1 mole of oxygen. So now I have mole amounts here. Oh, I actually have to calculate this now. 72.4 divided by 55.845. 1.296 moles of iron is in my sample, and then 1.725 moles of oxygen is in my sample. Great. So with these numbers, do I just round iron down and oxygen up? Is this iron O2, FeO2? Can I just round those things? Nah. Once you have mole amounts, what's the trick? Divide by the smallest one, because if you do that, you just force one of the numbers to be a whole number. And so in this case, it's iron. If you divide both numbers by 1.296, we'll have nicer looking numbers. Divided by 1.296 equals 1.33 moles of iron and 1.33 moles of oxygen, 1 mole of iron. Great. So now can I round my oxygen down to 1 and just say FeO? No. How can I turn this into an empirical formula? Multiply by 3. Do I just multiply oxygen? No, you multiply both of them. So it's going to be Fe3O. What? 4. Okay. Good. Magnetite. Neat. I like questions like these. Those are like my plug and chug questions. Yeah. So this is our empirical form. Yeah. Probably 2.5 or 7.5, because you'd still multiply by the same factor. Or yeah, probably 2.5. I think in one of them I made it like a 7, and I didn't like that. What's 1 divided by 7? Yeah, or maybe it was like 8 or something. Yeah. No, I will make it obvious. I'll make it obvious. Okay, so this is our empirical formula. What if, although this isn't a good example of it, what if I asked you for the molecular formula? Molecular formula. What would you do different? Well, one, I would actually have to give you an extra piece of information. I would have to give you the molar mass, right? And so if I asked you for molecular formula and gave you a molar mass, you would go through the exact same steps. You would get your empirical, weigh it using your periodic table, and then just figure out how many units you need to build up to that full molar mass. That's it. So I group those two kinds of questions together. Yeah, I like questions like this. It's like plug and chug. Okay. Okay. All right, the empirical formula of this, oh yeah, look, we're doing it right now. The empirical formula of a substance is that. So they just gave us the empirical formula. They already did the percent analysis for us. There's the empirical formula. The molecular weight is blah. What is the molecular formula? So this is exactly what I was saying, that we're given the empirical at C6H5NO2. All right, they're telling us, so that's empirical. They're telling us the molecular weighs around 300, around 370 AMU. So they want us to report the formula for it. So if I compare the weight of the empirical to the full molecule, I can figure out what that multiplier is. So this doesn't have to be super perfect. You can just do like back of the envelope type of calculation. So there's 6 carbons, so it's 6 times 12. Plus 8 hydrogen, so plus 5, plus a nitrogen, 14, plus 2 oxygen, so 2 times 16. We don't have to be like super, because we know it has to be a whole number. We can't have like a fractional multiplier. It has to be a whole number. 6 times 12, plus 5, plus 14, plus 32. 123 AMU. So what is our multiplier? 370 divided by that. It's 3. Good. So it's 3. All right, and so that means we just multiply our empirical by that same multiplier. Right, so then our molecular will be C18H15N3O6. And so, this question can be combined with the previous question. So this would be an easier one where I just give you the empirical, but I could instantly make number 19 harder by putting those two things together. Make you get the empirical first, then report the molecular if I give you the molar mass. Okay. All right, next one. Okay, yay, molar mass stuff conversion. Okay, 2 moles of CH4 contains how many hydrogen atoms? So I give you mole amounts. So mole means what? 1 mole of anything equals 6.022 times 10 to the 23 particles. You need to memorize that. You need to memorize that. So if I start with 2 moles of CH4, I can use that mole conversion to figure out how many molecules of CH4 I have. So 1 mole of CH4 is 6.022 times 10 to the 23 what? Hydrogen atoms? No. CH4 molecules. Molecules. So how can I get now to hydrogen atoms? Divide by 4? Multiply by 4. Yeah, how, if you were in like the unit of bikes right now, and I ask you how many how many total tires do you have? All right, so the equality here is 1, molecule of CH4 equals 4 H atoms. So I'm going to put that 1 on the bottom. 1 molecule of CH4 is 4 hydrogen atoms. So the formula gives it to us. Cool. So let's keep going. How much does 2.95 times 10 to the 24 CO2 molecules weigh in grams? So I am giving you molecules. We want to figure out how much it weighs in grams. If we use the periodic table, what's the unit on the periodic table? That's useful for us. It is, molar mass is not a unit. It's grams per mole, yeah. So if you look at carbon says is 12.01. It means that 1 mole of carbon weighs 12.01 grams. So if we add this up for CO2, 44.01 grams of CO2 is 1 mole. That's if you calculate the molar mass. I'll just give it to you right there, 44. So that's off the periodic table. So if we start with molecules, we got a problem. CO2 molecules, because our molar mass is in the unit per mole. So I need to convert that molecule to mole. So we can use the conversion of Avogadro's number again. So 6.022 times 10 to the 23, but this time it's going to be on the bottom because we're going from molecules to moles. So now we're in 1 mole of CO2, and now we're home free. Now we can use the molar mass. 1 mole of CO2 is 44.01 grams. And that's the answer. And hopefully, yeah, the answer's there. Okay. I'm going to do one more because I didn't have that included here. So I'm just gonna ask you a question. What if we had 1.25 times 10 to the 24 hydrogen atoms? How much, and this was of CH4. If we had a sample of CH4 and it had that many hydrogen atoms, how many grams would it weigh? And I'll tell you, the molar mass of CH4 is 16.04 grams per mole, I think, something like that. Where would we start? Where would we start? Go to moles? You want to go to moles? Okay, so where would I put the 6.022? On the bottom, okay. 6.022 times 10 to the 23 H atoms is 1 mole of what? Of what? Hydrogen, yes, of hydrogen atoms. Okay. This is fine. The way he's doing is fine. We want to get to grams of CH4. Yeah, where does the 4 go? On the bottom, yeah. There's 2 tires on every bike. Yeah, so we're going to put 4 moles of hydrogen on the bottom and work our way up to 1 mole of CH4 on top. Yay! Because now we're in a unit that we could use molar mass. Now we're in units of moles of CH4. So now we can use that molar mass. So just times 1 mole is 16 whatever grams. Right? So this one's a little bit tougher. I don't know, if I gave you like 10 grams of CH4 and I asked you how many hydrogen atoms it was there, you'd give it to me no problem. But as soon as I give it to you backwards, you guys like freak out. It's literally just the backwards problem. Yeah. You tell me, is multiplication and division commutative? It doesn't, yeah, so yes, it does, and I knew that's why you were whispering, but I knew either method works. Whether you do the divided by 4 first, or you do Avogadro's number first, the difference is you would say 4 atoms of hydrogen is just one molecule of CH4, and then you would do, okay, 6.022 times 10 to the 23 CO2 molecules is 1 mole of CH4, and so you see it's the exact same thing. So it's whether you're talking about mole amounts or single molecules, it still works, because when we looked at chemical equations like this one, right, we're saying 1 molecule of this reacts with 3 molecules of this to give 2 of that, 3 of that, or we can say 1 mole of this reacts with 3 moles of this. We have 2 and 3. And so remember, mole is just like a counting number. And so mathematically, you see that these 2 processes are the exact same. That's good. Yeah, it doesn't matter what order you go in. I don't know how you were thinking of it, doing it, but just do whatever works for you. Yeah. Okay, so I wanted to do that one. All right, we have 30 minutes left. Jeez. Can we do some hard ones? Okay. Which one? Or does anyone want to suggest one? 30? Oh. Actually, no, I don't want to do that one. Because I yeeted that question out of the lecture slides. And so it's not going to be assessed on the exam. Let's do this one. Let's do 29. Let's just work backwards then. You titrate a gram amount of an unknown monoprotic acid with 11.42 milliliters of standardized sodium hydroxide with a concentration of blah. What is the molar mass of the unknown monoprotic acid? So it's asking for molar mass. When I don't know what to do, the first thing I do is look at units. Molar mass has a unit of what? Grams per mole. So if I figure out the gram amount of HA, of my monoprotic acid, because that's the molar mass I want, and I figure out the mole amount of HA I have, then I can get the molar mass. Do I have any of these already? I have the grams. Fantastic. It's halfway done. I just need to figure out how many moles of HA I have. And so I'm going to use the rest of the information. So it says that I'm reacting this much strontium hydroxide with a certain concentration. So I'm going to write the balanced chemical equation to see if there's stoichiometry involved here. So this is an acid-base neutralization. So I have just strontium hydroxide reacting with HA. The H is the acid. So what's the ratio here to acid to base? 1, 2, 2. I need 2 equivalences of acid to neutralize 1 equivalence of base. Because you can think of the base as the hydroxide. There's 2 hydroxides in this guy, so I need 2 H pluses to come from this guy. right? So it's a 1-to-2 ratio. Cool. So with that given information and the concentration of strontium hydroxide, that concentration of strontium hydroxide means there's 0.1245 moles of that strontium hydroxide in 1 liter of solution that is delivered. I did not deliver 1 liter, I delivered 11.42 milliliters. So I'm going to start with that number, 11.42 milliliters. I'm going to convert it to liters because I'm lazy. All right, that's of the strontium hydroxide. This is my known because it's standardized. So I'm using it as my like known amount of stuff. Then I can use that molarity, 0.1245 moles. Oh, nope, sorry, that number doesn't go down there. It goes up here. Sorry. 1 liter goes on the bottom. And then the 0.1245 moles of strontium hydroxide goes up top. Cool, now I'm in moles. Can I put that answer in my denominator? It's moles. It's not the same substance. Yeah, so how do I make it the substance I want? Do I just scratch it out? Why multiply? Two, yeah, to get, I need 2 HAs, yes. So strontium hydroxide, just 1 would be on the bottom, 2 HAs would be on top. Great. And that will give me the mole amount. That is what goes on the denominator. And then that's your molar mass. Okay. Do not forget the stoichiometry. Because you know for a fact I'm not going to give you a 1-to-1 ratio. Ever. But like, does it change that much, right? Like I've written a billion of these questions and literally all I do is change the substance, okay? Because what if I said, okay, we titrate an unknown diprotic acid. What if I say diprotic and it's H2A? How would this change? It would be 1-to-1, yeah. And then we wouldn't even need this step, suckers, okay? What if it was H3A and strontium hydroxide? Be weird. Hold on, I need to think about it. Think about all that changes is 3 and 2, right? So you would have a 3 and a 2, right? Okay, and then that mole amount goes up there. Same thing with titrations. This is what we got to think about, the actual chemistry that's going on. Do not do M1V1 equals M2V2, or I'll be mad. Yeah, don't do that. So let's do 1. Yes, okay. So here it requires this much acid with that concentration to neutralize 10 milliliters of sodium hydroxide. What is the molarity of sodium hydroxide? So this is a titration. But again, if you're confused, if you're lost, you don't know where to start, just look at the units. We want molarity of sodium hydroxide. So what's the unit of molarity? Moles per liter. But specifically, it's moles of we want molarity of sodium hydroxide, so that's our solute. So we need moles of sodium hydroxide, right? Because that's the solute, over liters of sodium hydroxide. Do we have any of these already? Yes. Which one? What number is that? The 10 milliliters. Yes, we already have that one. Yay. So we just need to figure out moles of sodium hydroxide. Does this sound familiar? It's just like the previous question. It's exactly the same. It's just it's going into a different unit now. So that means before we move on, we need to think about the chemical reaction that's happening. We're combining H3A and sodium hydroxide. So what is the ratio? 1-to-3. 1-to-3. So we are given a volume and molarity of the acid. So that's what I'm going to start with. So 0.01449 liters of the triprotic acid, H3A, is 1 liter is 0.1729 moles of H3A. I cannot put that answer into my denominator because the substances don't match. Okay. This one student I had was gung-ho about doing M1V1. And they're like, I'll just multiply by 3. It's a triprotic acid, I'll just multiply by 3. Don't worry, I know what to do. But do we multiply by 3 in this example? Oh yeah, we do multiply by 3. Okay, whatever. Okay, but if it was the previous question, we'd multiply, I don't know if we'd multiply by 3, but it would go in the denominator, right? And so, yes. Sometimes you divide by 3, you know? Okay, so what's the ratio that we put here? 1 to 3. 3 moles of NaOH is needed to neutralize 1 mole of H3A. This is like your the citric acid thing. This is exactly like the LLT, right? Because citric acid was a triprotic acid. No. Okay. And then whatever this answer goes up top, and you divide by the liter amount of sodium hydroxide. So you're dividing by 0.01000 liters. And then there's some answer there. So what about these pieces of information? What about these? What about that? We didn't need any of those. Yeah, so that's like the thing with molarities and concentrations. We oftentimes don't need concentrations. If we're just working with volumes and molarities, we can get mole amounts just from that. We don't need gram amounts. Cool? Yeah, all right. Okay, ooh, this is good one. What volume in milliliters of HBr is required to completely react with 0.155 grams of zinc? I'll tell you that the molar mass of zinc, I should have given this to you. Typically, if it's a chapter 4 question, I give you the molar masses. If it's a chapter 3 question, I don't give you the molar masses. FYI. That's why you come to the review session. Zinc is 65.39 grams per mole. So this is a chapter 4 question, so I should have given you the molar mass. And I would make a distractor. I'd give you the molar mass of HBr as well. But you actually don't need to use it. So it looks like we are given an amount of zinc, and we want to figure out how much HBr we need. Right? But how do I use that stoichiometry? I need to be in the unit of moles. So if I'm given zinc, I need to get moles of zinc. So how can I convert what's given to moles of zinc? Yes, molar mass. So I'm going to start with 0.155 grams of zinc. I'm going to use the molar mass, 65.39 grams is 1 mole of zinc. Now I got my ticket to go on the bus. What's next? Mole ratio, yeah, stoichiometry. So 1 mole of zinc is 2 moles of HBr. So now I know exactly how many moles of HBr I need to do this reaction. But is that my answer? No, I want volume. So they give me a molarity. I don't like big M. I always like to rewrite it as the equality that helps me relate the meaning of that unit. So if I rewrite that, it means that there's 0.265 moles of HBr in what? 1 liter of solution. So how am I going to set this up in the next thing? On the bottom, yeah. So 0. Like, do you know intuitively that you have to divide by molarity? Like, given the stuff? No, I don't. I'm not smart enough to do that. But if I rewrite molarity to tell me exactly what it's relating, then I can see, oh, I need to put moles of HBr on the bottom. So yes, that goes there, and then 1 liter goes up top. All right, and then multiply by 1,000 or whatever. 1 liter, 1,000 milliliters, there's our answer. All right, so in this question, I gave you a gram amount of a reactant, and you figured out like a liter or a molarity of the other reactant. In the titration, both of them were solutions. Both of them had concentrations. 27 and 28, they're very similar to one another, right? It's just different ways we get moles. In all cases, we do like some type of mole conversion, right? Like either use molarity or grams to get moles. We do stoichiometry, then we do another, you know, gram or mole conversion at the end. It's very repetitive. Okay, keep working backwards. All right. Okay, is this the same reaction? No, okay. Using the following balance reaction, this reaction is completed with 61% yield and 85 grams of aluminum is collected. How much magnesium in grams must have reacted? Great. So, percent yield. I think I gave that to you. Actual over theoretical times 100. So this 85 grams is what? It's the actual. It's what I actually collected. All right, and this is equal to 61%. So you did this reaction, you only, were able to isolate 61% of your product. That's 60, and you only got 85 grams. That means you put enough stuff into the reaction vessel to gain more, but you didn't get all of it. So we need to calculate the theoretical yield, what you would have aimed for. So it's just rearranging things here. So, 0.65 or 61, I don't want it to be a percent, I want it to be a fraction, is 85 grams over your theoretical. So with 60, basically efficiency, 61% efficiency, move things around, okay, 85 divided by 0.61, you need to aim for 139 grams of aluminum in order to fall among 85 grams with a 61% yield or like efficiency. So this is what we're aiming for. Our theoretical yield is what we use with stoichiometry. So the idea here is we're basically given aluminum, we need to work our way back to how much magnesium we need. So this is going to be an example of we're given grams, we use molar mass, we do stoichiometry, we use molar mass again of the thing we want. So 139 grams of aluminum. I need to use the molar mass of what? Aluminum. I can't just pick whatever the heck I want. It has to be aluminum. What? No. 26.98. See, this question, I give you all the molar masses. It's chapter 4 question. Okay. Is 1 mole of aluminum. Great. Next, now what? We need to get on the bus. Get on the bus, because we're in the unit of moles. Now we can do stoichiometry. All right? So we can use the coefficients. 2 moles of aluminum goes on the bottom, 3 moles of magnesium goes up top. Yay. And then now we use the molar mass of magnesium. Yes, 1 mole of Mg is 24.31 grams, and whatever that answer is. So whether you did the stoichiometry first or second, so we did it second. We calculated theoretical first, then plugged that into all this work. If you did it backwards, like if you put 85, worked your way through, then put it into actual, calculate theoretical, you would still get the same answer. It's just, are you applying that 61% before or after this stoichiometry? It's not a big deal, but you do. So yeah, the big idea here is you need to put in more magnesium than you initially thought or thinking because your efficiency is crappy. You gotta put in more. Okay, all right, let's keep going. All right, so we have a 3.82 gram sample of magnesium nitride. It reacts with this much water. The yield of magnesium oxide is blah. What is the percent yield of this reaction? So it's another percent yield. So that 3.6 is what? Actual or theoretical? Actual, yes. Because how do we get the theoretical? By the experimental conditions. Very good. I'm so smart. Yes. but crap, they give us two different amounts. So how do I get the theoretical? Do I just pick one and convert it? No, we got to do both of them. We got to figure out which one's limiting. So the idea here is there's two products. So you might be thinking, well, which one do I move to? Do I convert magnesium nitride to ammonia, or do I move it or convert it to magnesium oxide? Me, I'm lazy. Since I know percent yield is in mole or in grams of magnesium oxide, I want to convert both of these reactants to how much magnesium oxide I make, because then I can plug those the actual number straight into percent yield to get my answer. So, all right, so let's do this. So we need to do two stoichiometry setups. So I'm going to just start with the magnesium nitride first because it is written first. Mg3N2. And I hope by now you see we've done a ton of molar mass, stoich, molar mass, and that's what we're doing here. Nothing different. So we're in grams of magnesium nitride. So what molar mass do we use of magnesium nitride? Yes. So 195 on the bottom, 1 mole of Mg3N2. Now I do stoichiometry, so 1 to 3 moles of MgO is 1 Mg3N2. Now I'm in moles of magnesium oxide, so I use the molar mass of magnesium oxide, so 1 mole is 40.30 grams. Boom. All right, but now I need to look at water too. I need to see, okay, if all of the water reacts completely, how much do I get out of it? So this is water, so we do the same thing, but using the information with water. So 18.02 grams is 1 mole of water. Stoichiometry says 3 moles of water is 3 moles of MgO, and then molar mass of MgO again. There we go. And then you plug it into your calculator. Does someone have the first one? Or do I have to do it? The first one? 4.5749 grams of MgO. And then what's the second one? 29 grams of MgO. So which one matters to us? The which one? The first one, yes. But is that my answer to this specific question? What did we just calculate? When I circled the smaller one, that is my theoretical yield, yes. That is the maximum this reaction can make given the conditions that I put in it, but with the assumption that 100% of it reacts and we get product. But the thing is that we didn't collect all that product. So this number becomes the denominator and you calculate percent yield. Sig figs. How many sig figs should my theoretical yield have? 3. Probably 3. Because the value we started with had 3. Also, stoichiometry, how many sig figs is in here? Are you thinking, there's 1 sig fig here? It's infinite. Yeah, coefficients are infinite. Good. All right, so yeah, stick that in. That's theoretical. And then you get your percent yield. All right, how many grams of the excess reactant is present once the reaction is complete? Yikes. We already finished the determined which was the limiting reactant in this question. What is the limiting reactant? The first one, the magnesium nitride. So the idea of the limiting reactant is that amount decides how much product you have, but it also decides how much reactant of the other reactant you consume. So I'm going to take that same amount, that magnesium nitride. I'm actually just going to copy it because I'm lazy. All right. The mole amount of magnesium nitride that reacts is what's going to dictate how much water I consume. But I just use different stoichiometry here. I'm going to do the 1 to 3 ratio to get to water. So I'm saying, okay, all of the magnesium nitride is consumed. So for every 1 mole of Mg3N2, I have to consume 3 moles of water. And then I need a gram amount. So 1 mole of water is 18.02 grams. And then I'm going to beat you to it this time. 3.82 divided by 100 times 3 times 18.02. That I consume 2.045, go away, grams of water. Is that my answer? No. How do I get the excess amount? Subtract it from which number? Yeah, 7.73. So once you subtract, you'll get how much is left over. 5.68 grams of water is left over. Is that what the answer is? I hope so. If you picked the wrong limiting reactant, what's going to happen? You accidentally said, oh no, all the water reacts. You're going to do all of this and you're going to subtract and you'll get a negative number. And that's how you'll know you picked the wrong one. Okay. All right, we have 8 minutes left. Is there a certain type of question? Wow, we did actually, did we do everything? We almost did everything. What? Oh, well, we don't need to do 30. Okay, here. Okay, let's do 23. We have a 5-gram sample of sodium sulfate diluted to 500 milliliters. What is the concentration of sodium ions? 23, yeah. So sodium ions, right? We want sodium plus ions, the concentration, molarity, right? Molarity is moles per liter. So sodium plus ions is going to be moles of sodium plus over liters of solution. Right? So do we have any of these pieces of information already? Yeah, we have the liters. Yeah, 500 milliliters. Yeah, okay. We just need to figure out how many moles of sodium are present. But they give us gram amounts. So I need to convert that to mole amounts. So 5 grams of sodium sulfate. Dang it. What happens when I don't write a key? 22.99 times 2 plus 32.06 plus 4 times 16. The molar mass of sodium sulfate is 142.04 grams per mole. All right, so we have a gram amount of sodium sulfate, so 142.04 grams is 1 mole of sodium sulfate. Great, I'm in moles. Can I just put that in the numerator? What's wrong? What's wrong? Wrong moles. Yeah, so how can I get it to moles of sodium? There's 2. Yeah, if this was a net ionic equation question, would you split sodium sulfate? Yes, you would split it, but you would get how many sodium plus out of it? You would get 2 of them. So we do one more step. For every 1 mole of sodium sulfate, you get 2 moles of Na+. And so that will tell you how many moles of sodium plus there are. So it's 0.0704 moles of Na plus are present, so double the amount of moles of the solid. And then just divide by the liter amount, so 0.5, a bunch of stuff. So like 0.14 something. Is that the answer? Yeah, something like that. Good. That's our answer. So be cognizant of the unit, the concentration unit that's asking for. It's not asking for molarity of sodium sulfate. If it was asking the molarity of sodium sulfate, we wouldn't do this last step. We would just divide this answer by 0.5 liters. But because it's sodium, we need to multiply our molarity by 2 because there's 2 sodiums per sulfate. So if I had sodium, or no, I'll just do this one. If I had magnesium bromide concentration, and it was 1 molarity. What's the concentration of bromide? 2 molarity, yeah, yeah. Right, because there's 2 bromides for every 1 magnesium bromide. Okay, what if I had a solution of aluminum chloride and I told you that the chloride concentration was 6 molarity? What's the concentration of aluminum chloride? 2, yes, yes. Right, because all of these are strong electrolytes. All right, we have 4 minutes. Okay, I guess we'll just finish it. So, okay, how many milliliters of this concentration HCl should be diluted to a total volume of 5 milliliters to prepare this concentration of HCl? 24? So we finally can use M1V1. You're finally allowed to, because this is a dilution question. So 1.5 is M1. Total volume is V. So 50 milliliters is what? V, given the context. V1, V2, V2, yes. And then the diluted molarity, that's M2. So we're calculating for V2, or sorry, V1. All right, and just plug and chug. So V1 times 1.5 molarity equals 50 milliliters times 0.125 molarity. So what's the unit of V1 that comes out? Milliliters, yeah. And so the answer is 4.17. So what would this look like? You guys used a volumetric flask, right? So you would pipette 4.17 milliliters of this HCl, and then you would dilute the whole thing to the 50.0 milliliter line. That's how it would work. And then that new diluted 50 milliliter solution would have this concentration, 0.125 molarity. That's how you do it in lab. We're done? Well, I guess we have 2 minutes left, so we'll just do the one we didn't do. Classify the following as a mixture, pure substance, or pure substance. If it's a mixture, it's or I can't read. Okay. Rust, what is it? Is it pure or is it a mixture? It is pure. Specifically, what kind of pure substance is it? It is a compound. Compound, because there's more than one element present. Okay, what about steel, which is 2% carbon, 98% iron? It would be a mixture, yeah. What kind of mixture? Hetero? It should be homo. I mean, in a perfect world, yes, it should be homogeneous, but it should be homogeneous. How did you identify it was a mixture? It has 2 elements there. Why can't it be a compound too? It's not a formula. It's just like percentages. Yeah. Aluminum. Then what kind of pure substance? Element. Okay. Sodium nitrate aqueous. You sure about that? It's in water. Yeah. Oh, yeah. So I didn't write sodium nitrate solid. I wrote sodium nitrate aqueous. Aqueous implies it's dissolved in water. So this is a mixture. So remember, all of the solution chemistry we talked about, that was all mixtures. Yes. So this is actually a mixture and it's homogeneous. So this one's tricky, right? Because you're thinking, but Dr. N, there's a formula there. But there's also another formula behind the scenes. Water. There's H2O all around there too. Okay. The air we breathe. Also a mixture, also homogeneous, because I can point to a bunch of different compounds that are there that make it up. The Atlantic Ocean, including the marine life. Yes. Hetero. Yes. Good. All right. So yeah, here my tips is if it's a pure substance, you can represent it with a formula or a symbol of some kind. It's a mixture if you have to use different symbols, but specifically they're not chemically combined, because like in sodium nitrate, there's sodium nitrate, but there's also water, but they're not combined. I could, in theory, separate them, and that's what makes it a mixture. All right. Happy studying. Do the practice exams. Do all of them, because it's free, right? There's 3 of them. All of your classmates will have access to them. It'll be a shame if you didn't do all of them. Okay. Any question? There's only 2 people here, Andrew and Brandon. Any questions before I go home? No? Then I'm gonna kick you out. You're welcome. Good luck.